So what I'm going to move on to in this lecture is a notion that we'll be meeting a lot of the time over many different parts in the remainder of the module. And this is a structure which is called a polynomial, and in particular we are interested in the properties and manipulation of polynomials. So at the end of the last lecture, we saw that there are certain structures, certain numbers, which cannot be described as rational numbers. They are what are called irrational. So for example, we have quantities such as the square root of 2. We cannot define the square root of 2 as the ratio of a whole number to a natural number. Similarly, we cannot describe the cube root of 20 as the ratio of a whole number to a natural number. What we can do, however, is describe these quantities as solutions to what I'll refer to as an identity, as a solution to a particular functional equation. So how do I do that? In other words, what do I mean by that? That is, as a value of some variable x for which a given function, which I'll denote by p of x, this is a property that when we evaluate that function at this given place of interest, this will give us a result, give us the outcome 0. So a couple of examples. Square root of 2, we can describe that as a solution to the identity p of x equals 0 in the case of p of x being x squared minus 2. If we evaluate this when x is the square root of 2, square root of 2 squared is 2. We subtract 2 from that, we get 0. Similarly, for the cube root of 20, we can describe that in terms of this function x cubed minus 20. When we evaluate that function at the point 20 to the power of a third, 20 to the power of a third cubed, that's 20. We subtract 20 and we get 0. So this leads us to this important notion of what I'm going to be calling a polynomial, and the other aspect, the roots of a polynomial. So what is it we have in this case? In general, what I'm going to be referring to as a polynomial of degree k in a variable x. This is specified, this is defined by a collection of k plus 1, what are referred to as coefficients. And the way we denote those coefficients is as c sub 0 through to c sub k. If we look at the functional form of a polynomial, this is just a summation. So the polynomial of degree k in x, that's defined via, we sum, starting from n equals 0, the coefficient with index 0, up to k, the coefficient with index k, the result of multiplying the coefficient c sub n by x raised to the power n. And so what this results in is the coefficient, the teeth coefficient c sub t, that multiplies x to the power t when we evaluate this polynomial at some point alpha. The way we write that for the polynomial p of x being evaluated at alpha, this is written as p of alpha. So I'm going to say a little bit more about this notion of coefficient. The number types that we can choose the coefficients from a polynomial from, you can be any of the types we saw in the last lecture. The natural numbers, the real numbers, the rationals, the integers. We can also limit our choice of coefficients to finite subsets of some collection of number types. So for example, one important case is what's denoted by the integers sub m, and that corresponds to carrying using only the integers 0, 1 through to m minus 1, but all of the arithmetic is carried out modulo m. If we have a particular set of number types that we wish to focus on, suppose we denote that by h, then we use this notation h sub k of x, or in general h of x, and that describes all of the possible polynomials of degree k whose coefficients are drawn from this number collection h, this number set h. So I've used this term root of a polynomial. What do I mean by the root of a polynomial? Well, the root of a polynomial p of x, that's just a value, say r, which we can assign to x, and when we do that, when we evaluate this polynomial at some position x is r, then the outcome is going to be 0. That's what we mean by a root, a way of choosing a value for the variable of that polynomial which gives us the outcome 0. One important property, I'm not going to prove this by the way, is that if we take any polynomial of degree k, there are exactly k choices of x for which that polynomial will assume the value 0. In other words, any polynomial of degree k has exactly k roots. We denote these just by r sub 1, r sub 2, r sub k. Now, there's a reason why I am using round brackets and not set brackets. The roots, these k roots, they're not necessarily distinct. We may have some values for the roots of a polynomial which occur more than once. It is also possible, I'm not going to talk about this possibility at this part of the module, that will be later on in the module. It's also possible that some of these roots are not real numbers. As I said, we're going to look at that particular case later on in the module. So here are a few examples. Here we have a polynomial, x squared minus 1. It is degree 2, the highest power of x involved with a non-zero coefficient, that's 2. The roots of this polynomial, it has 2 roots, it's degree 2, and its roots are minus 1 and plus 1. If we set x to the value -1, we square that, then we get the value +1, we subtract 1, and the outcome is a value 0. The same thing happens if we evaluate that polynomial at the point x equals +1. +1 squared is again 1. We subtract 1 from that, and again we get the outcome 0. And we look at the polynomial of degree 2, which is given by x squared minus 2 times x plus 1. Again, this polynomial has 2 roots. However, both of those roots are the same. They occur, the root 1 occurs with what is called multiplicity 2. I'm not going to talk in depth about multiplicity. Again, if we raise x to the power 2, if we raise x equals 1 to the power 2, 1 squared is 1. We subtract 2 times 1 from that, we get the outcome -1. We add 1 to that result, we get the result 0. If we take this polynomial has degree 6, the highest power of x with a non-zero coefficient. That's that's the power x to the raised to the power 6. It doesn't matter. It doesn't affect the degree of this polynomial. There's the coefficient of x to the power 5 and the coefficient of x to the power 1 is 0. This is a degree 6 polynomial. It's degree 4 polynomial in which all of the coefficients of that polynomial are 1. So 1 times x to the power 4, 1 times x to the power 3, 1 times x squared, 1 times x, and the constant coefficient corresponding to x raised to the power 0, that is also 1. That's the degree 4 polynomial. We also have this class of cases which we're going to see a lot of later. This is a quadratic, a polynomial of degree 2, x squared plus 9, and we're going to meet the notion of what we mean by the roots of this polynomial, as I said, later on in the module. So, how do we manipulate these objects? What are the typical sorts of operations that we might want to perform on a polynomial? Well, for example, we might want to, if we're considering general polynomials, so we have p of x and q of x, and these have degrees m, and then these do not have to be the same. One thing we might want to do is add the polynomials together. How do we do that? Well, we simply take the coefficient of in p, or corresponding, say, to some power x raised to the k. They take the same coefficient, x for x raised to the power k in q, and we add them. So we add matching coefficients, and that gives the polynomial which corresponds to adding those two polynomials together. We want to carry out an operation which is called scalar multiplication, where what we are doing is multiplying the polynomial p of x by some constant value alpha. How do we do that? We simply take each coefficient, c sub k, in p of x, and we multiply that coefficient by alpha to get the outcome. We can also think in terms of multiplying two polynomials p and q. So the degree of the resulting polynomial, this is given by adding the degrees of the two individual polynomials. I'm not going to describe the detailed operation for polynomial multiplication. If you're interested, this is described in the textbook on pages 30 to 32. Similarly, I'm not going to describe the operation of taking one polynomial p and dividing it by another polynomial q. This is also well defined. Again, if you're interested in the process, I refer you to the textbook, pages 33 to 37. A very important operation, which we are going to be meeting on a number of parts of the module, is this operation of how do we find the roots of a given polynomial. So in many applications, we have this problem where we have to find values alpha for which some given polynomial takes a value 0. So for example, we see this we're going to meet this in differential calculus and in this topic of optimization theory. We're going to meet this in a subject called spectral analysis, where it occurs in image compression and web page analysis. If we're dealing with small degree polynomials, so polynomials of degree 2, quadratics, polynomials of degree 3, cubics, polynomials of degree 4, then it turns out we can do this directly. Again, I'm not going to talk in much detail about this. If you are interested, I refer people to pages 43 to 45 of the textbook. I'm sure many people here will already be familiar with the process of finding the roots of a polynomial of degree 2 for finding the roots of a quadratic. In general, though, this is quite taxing, quite an onerous activity. People are interested, I give some discussion of that on pages 37 to 43 of the textbook. A lot of the methods use quite advanced techniques from calculus. There is a very strong reason for looking at polynomials, and this is this idea of refining how we look at the real numbers. So suppose we consider polynomials whose coefficients are restricted simply to rational values. So we're looking at what I described earlier as Q with capital X, so polynomials which only are allowed to have rational coefficients. Now we've already seen that these values, the square root of 2, the cube root of 20, these aren't rational numbers, but we can describe them as the roots of polynomials which only have rational coefficients. And if we take any rational number, then it has a finite length description because it's a result of dividing a whole number, which is a finite length, by a natural number, also is finite length. So in principle, we could give a finite description of the square root of 2 just by describing it as the as the root of a polynomial with rational coefficients. So the square root of 2 is the root of a polynomial which has rational coefficients. And that description would be finite. So this motivates an interesting question. Is it possible to do this sort of process for every single real number? In other words, is it the case, suppose we are given some real number alpha. Can we construct a polynomial which is only rational coefficients, but that polynomial has this real value alpha as a root? Now, if we could do that, that would mean we could give a finite description for any real value just by describing the coefficients of a relevant polynomial for which that value was the root. So in some ways, that would address this issue that I raised of computer systems only being able to work with approximations to real numbers. In principle, if we could carry out this process for any real number, we could work with arbitrary precision, real arithmetic, in terms of manipulating polynomials with rational coefficients. And unsurprisingly, it isn't possible to do that. There are real numbers which we cannot define as the root of some polynomial with rational coefficients. This is a very famous result. It was dates back to 1882, and one famous example is the value pi, the ratio between the circumference and the diameter of a circle. We cannot describe pi as the root of a polynomial with rational coefficients. So just to summarize, we're going to see polynomial structures very often in later parts of the module. We're going to meet them in calculus and when we talk about optimization. We're going to meet them when we talk about complex numbers. We're going to meet them when we analyze matrix properties, and in all of those areas, this problem of root finding is going to arise.